I hope you can do that. Okay, I'm happy for people to ask questions during the talk. That's fine. I'll try and keep an eye on the chat, but you can call out if you have something that you want to ask me. Perhaps I'll start by apologizing. I've had COVID, and I'm feeling much better now than I was a week ago, but my voice is still a little rough around the edges, so there is a risk that it will run out during the talk. So we may end up just all sitting here silently reading while I display my slides. Apologies if that happens. Okay, so as Philippe said, I'm going to talk about geometric invariant theory for reductive groups over non-algebraically closed fields. This is, there we go. The idea is you have a reductive group over an arbitrary field acting on an affine variety. That's the context in which I mean geometric invariant theory for this talk. And I want to concentrate on particular on studying the structure of the orbits. So there's a very well-known result in geometric invariant theory called the Hilbert-Mumford Theorem. I'll recall it briefly a bit later on, which tells you when an orbit is closed in terms of taking limits of cocharacters. So that's the idea that this approach to non-algebraically closed fields is centered around. Another important idea, the notion of an optimal destabilizing cocharacter. I'll come to this later, but just very quickly, if an orbit is not closed, that means that there's a cocharacter that will take you out of that orbit by taking the limit. And we say such a cocharacter is a destabilizing cocharacter, and the word optimal means that there's a way of finding somehow the best cocharacter that does this, and this turns out to be a useful thing to do. And then towards the end, I'll talk about the interplay of this geometric invariant theory with the theory of spherical buildings and also the theory of G-complete reducibility, the theory of G-completely reducible subgroups of a reductive algebraic group. And what I'm talking about is joint with Michael Bate and Gerhard Röhrler, some of it with Rudolf Tanger, and some of it with Sebastian Hörpel as well. So here's a rough plan of the talk. First, I'll remind you what happens over algebraically closed fields, the Hilbert-Mumford theorem, and I'll talk a bit about these optimal destabilizing cocharacters. That's not so well known. The Hilbert-Mumford theorem, I think, is very well known. And then I'll talk about the extension to non-algebraically closed fields. And this involves the idea of what we call cocharacter-closed orbits. So I'll give some definitions and then look at some properties of this notion of cocharacter-closure and some results and a couple of open questions. Then I'll start talking about spherical buildings and how you can use some ideas from the theory of spherical buildings to say things about geometric invariant theory. So a reductive algebraic group over an arbitrary field has a spherical building attached to it, built out of the parabolic subgroups of the group. And this turns out to be quite useful to look at when you're studying the geometric invariant theory. And then as an application, I'll talk a bit about G-complete reducibility. So I'll tell you later on what it means for a subgroup of G to be G-completely reducible. And then I'll finish. Everything up till now is 5 years old or more. Some of it is nearly 10 years old. So I'll finish by talking about something much more recent, which is the notion of a spherical edifice. And basically, this is what you get if you try to copy the construction of a spherical building, but with a non-reductive group. So I'll say just a little bit about that at the end. So just a bit of background and notation. So K will always be a field. By a linear algebraic group, there are different approaches to the notion of an algebraic group over a field, or a group scheme over a field, a smooth group scheme over a field. There's this very modern language which you see for instance, in the book on pseudo-reductive groups by Conrad Gaber and Prasad. And then there's an older language, which is what you see in the classic books on linear algebraic groups by Humphreys, Burrell, and Springer. So I'm going to use this older language. So to me, a linear algebraic group G, it will be a linear algebraic group over K bar. K bar is the algebraic closure of K, together with a choice of K structure. So really, this is just a matter of language, but I wanted to say something here because it's easy for people to get confused. So when I talk about a subgroup of G, I mean a K bar defined subgroup. If I want to say a subgroup that's defined over the ground field K, then I'll say a K subgroup or a K defined subgroup. Okay. I'm a bit old-fashioned also when I talk about centralizers and stabilizers. I mean these in the set theoretic sense. So the centralizer of a subgroup H of G, that's the group of K points of G that commute with all of the K points in H. So I regard this as a set theoretic object rather than as a scheme theoretic object, which in some ways is a more natural way to look at it. But what that means is that when I talk about the centralizer, even the centralizer of a K-defined subgroup need not be K-defined. It will only be defined over the algebraic closure K bar a priori. And then a bit of notation at the bottom. If I have a subset of G of K bar, the set of K bar points of G, a subset H, then I just defined H of K to be H intersect the K points of G. So I'll sometimes write that, and I'm not saying that H is K defined or even a variety when I use this notation. So our setting is G is a connected reductive group over a field. Pretty much everything I say makes sense for non-connected reductive groups as well, but just to keep the discussion a bit simpler, I'll stick with the connected case. And X will always be an affine variety over the same field K on which G acts. And then a bit of notation there, I'll write G of K dot X for the orbit and G sub X to mean the stabilizer, where X is a K point of G. Again, quite a lot of what I'm saying makes sense if I look at arbitrary K bar points of X, but just to make the discussion simpler, I'll stick to K points. So some examples. Well, you can take X to be G and you can look at the action of G on itself by conjugation. To generalize this, and this is something that we'll come back to later on when we talk about G-complete reducibility, you can look at the action of G on X equals G to the N, this Cartesian product, by simultaneous conjugation, according to the formula down there. So if you have an N tuple G1 up to Gn, how do you act on that with some element little g of the group big G? You just conjugate all of the elements in the tuple by this little g. And then another familiar example, the adjoint action of the group G on its own Lie algebra. I'm not going to be looking at this example later on, but it's one of the standard ones. Now I want to talk about cocharacters. When I say cocharacter, in keeping with the convention I was talking about before, I mean K bar defined cocharacter. So what is a cocharacter? It's a homomorphism lambda from the multiplicative group of the field. That's what the notation GM means, to G. And we write Y of G for the set of all cocharacters. And there's an action of G on Y of G. If we have a cocharacter lambda and an element little g of big G, then we define little g dot lambda according to the formula there. Easily check that that's another cocharacter. Now I want to remind you of what a limit means. So take some point little x in, I should have written capital X of K for consistency, never mind. And pick a cocharacter lambda. I probably should have written that down explicitly as well, sorry. And then we can define a morphism from GM to X by the formula there, psi X of A as lambda A dot X. Now GM, we can think of as the non-zero elements of the field, is sitting inside affine one space, the whole of the field. And so we can ask whether this morphism psi x extends to a morphism psi x hat defined on the whole of the affine line. And if it does, then we say that the limit as a goes to 0 of lambda a dot x exists. And I've spotted another typo there. That dot shouldn't be sitting on top of the x. It should read lambda a dot x. Sorry about that. And in this case, we say that the limit x prime is the value of psi x hat at 0. So this limit may or may not exist. I'll go through an example now. I'm going to write this down on a separate, on something separate. So I'll stop the share for a minute. Can you all see that?
Yes, we see it. We see it.
Yes. So my group G will be SL2, and I'll take X to be SL2, and I'll look at the conjugation action. So let's define a co-character lambda by lambda of A is the diagonal matrix A0, 0, A inverse. And let's first of all take X to be 1, 1, 0, 1. So let's ask ourselves whether the limit exists for this particular lambda and this particular X. So the limit as A goes to 0, lambda A dot X. So this is going to be the limit as A goes to 0. So lambda of A is A0, 0, A inverse. Oops. And the action here is the conjugation action. So I get this. I do the matrix multiplication, and I get 1a squared 0, 1. And then I hope you'll all believe me when I say that the limit as A tends to 0 of this is just the identity matrix. So in this case, the limit does exist, and it's equal to the identity matrix. Let's do another example. Same G, same lambda, different X. So now take X to be, let's do the lower triangular guy this time, and look at the limit as A goes to 0, lambda A dot X. So we conjugate this matrix by A0, 0, A inverse. And we do the matrix multiplication, and we get 1, 0, A to the minus 2, 1. And this limit does not exist. Essentially because A to the minus 2 is not a polynomial in A. I think it's quite useful to see one or two examples like this. The definition of limit, if you haven't seen it before, looks a bit fearsome and technical, but actually everything boils down to calculations like this, and you end up with powers of A, and you're just looking at whether you have positive powers or negative powers. So back to the slides. That's the example I've just done, the blank example here. Another example, take a cocharacter lambda of G. We define a subgroup P lambda. I'm going to tell you what its K points are. It's all of the G's in G of K, such that the limit as A goes to 0 of lambda of A, G lambda of A inverse exists. So this limit will exist for some G's and not for other G's. You look at all of the G's for which the limit exists. It turns out that this is a parabolic subgroup of G, and every parabolic subgroup arises in this way. So this is quite well known. You can see this construction in Springer's book on linear algebraic groups, for instance. So now, until further notice, let's assume that our field is algebraically closed. And so now I'm going to remind you of the Hilbert-Mumford Theorem, or HMT for short. So take some k point x, look at the closure of the orbit, g of k dot x, so that bar over g of k, that bar there means the closure. Can you see the cursor when I move the cursor? Good. And the Hilbert-Mumford Theorem says that there's a unique closed G orbit O contained in the closure of the orbit. The existence of at least one, that's very easy to prove. That's just a very straightforward dimension argument. You just take an orbit of minimum dimension in the closure. The fact that there's only one is harder, and that you need the group G to be reductive for that. But then the second part of the theorem says that there's a cocharacter that will take you to that closed orbit. There will be a cocharacter lambda such that the limit as a goes to 0 of lambda a dot x exists and belongs to this closed orbit O. Very useful practical criterion for determining whether an orbit is closed or not. Well, what about if the orbit is already closed? If the orbit is already closed, then your unique closed orbit in the closure is just the orbit itself. And what do you take for the cocharacter? You just take the trivial cocharacter. So when I say lambda equals 0, I mean the trivial cocharacter that just sends everything to the identity. We tend to write cocharacters using additive notation rather than multiplicative notation. So the theorem is true even when the orbit is already closed. And now we get as a consequence of this, the following equivalence. The orbit g of k dot x is closed, that's part one, and part two says that the orbit is closed under taking limits of cocharacters. So an orbit is, the Hilbert-Mumford theorem says that an orbit is closed if and only if it's closed under taking limits of cocharacters, and if it's not closed, there is a cocharacter that takes you to the closed orbit. So this is the idea that we want to try to generalize over an arbitrary field. Just before I go on to that, one more result I want to mention. So BMRT, B is bait, M is Martin, R is Röhrler, and T is Tanger. So you'll see BMRT and also BHMR appearing later on. The H is for Herpel. And this result says, suppose you're in a situation where you have a point X and a cocharacter lambda. Suppose the limit exists and it's still in the orbit that you first thought of. So that tells you that your x prime is conjugate to your x by some element of g of k. But this result says that it's actually conjugate by some element of the unipotent radical of p lambda. So this notation here, RU of p lambda, that means the unipotent radical. Remember that p lambda is the parabolic subgroup associated to this cocharacter lambda. This result is not so well known, I think, even over algebraically closed fields. Now let me talk about optimality. So the result I'm going to give you is a combination of ideas of Hesselink, Kempf, and Rousseau, who all came up with similar constructions independently at around about the same time. So I'll refer to this result as the optimal Hilbert-Mumford theorem, optimal HMT. So take some point little x, such the orbit is not closed, and let O be the unique closed orbit contained in the closure of the orbit that you first thought of. Now, the Hilbert-Mumford theorem says there's a cocharacter lambda that will take you from X into this orbit O, okay? What this optimal version says is that there's an optimal lambda that does this, something I call LambdaOPT. Okay, now this is still a bit vacuous because I haven't really told you what optimal means, and I'm not going to tell you what optimal means because it's a bit technical. But one part of the consequence of being optimal is that this cocharacter is canonical in a certain sense. So this means that it's invariant under any automorphisms of the setup that happen to be lying around. This turns out this turns out to be really useful. The word optimal comes because you construct lambda by actually optimizing a real valued function over some set, optimizing in the usual sense of optimization theory. So we call that LambdaOPT the optimal destabilizing cocharacter. I use the word the, which suggests that LambdaOPT is unique. Well, it's not quite uniquely determined, but it's determined up to conjugacy by points in the unipotent radical. In particular, the parabolic subgroup P LambdaOPT, or P-opt for short, is uniquely determined. And the most useful consequence of optimality is that this optimal parabolic P-opt contains the stabilizer of X. Turns out to be really useful. So just one application of that in the context of G-complete reducibility. I guess I'm getting things a bit out of order here because I haven't told you what G-completely reducible means. I will give you the definition a bit later on. But using this idea of an optimal destabilizing cocharacter, you can show that suppose H is a subgroup of G and N is a normal subgroup of H. If H is G completely reducible, then N is also G completely reducible. Okay, and that answers a question asked by Sarah. If G is GLN, then G completely reducible just means reducible in the usual sense of representation theory. So this result that I've quoted here is a generalization of Clifford's theorem in representation theory, which says if you take a representation of a group and restrict it, a completely reducible representation of a group, and restrict it to a normal subgroup, then the restriction is still completely reducible. So now let's move on to talking about what happens over arbitrary fields. So from now on, K will be an arbitrary field. So how can we understand the structure of the orbits? Is there a Hilbert-Mumford theorem? Does it make sense to talk about Zariski-closed orbits anymore? Well, I mean, it makes sense to, but in some ways it's not a very natural notion. So I'm going to present a different notion and try and persuade you that it's useful. What happens if our field has extra structure? So for instance, what if we have a valued field which has a natural topology on it, a strong topology? So then we can ask whether an orbit is Zariski-closed. We can also ask whether it's closed in the strong topology, because any affine variety over K will then inherit a strong topology from the field. So Bremigan looked at some of these ideas over local fields of characteristic zero. He was interested in whether certain orbits were closed or not. And back in 2020, similar questions for valued fields. So I'm not going to answer these questions directly, but I just want to say our philosophy is that it makes sense to look at what happens for just a bare field with no extra structure on it. Once you've got that figured out, once you can say what's happening for just the field by itself, then you can start thinking about what happens if you put extra structure on your field. So maybe this is a useful approach. So we'll define Y sub K of G to be the set of K-defined cocharacters. So Y of G is the set of all cocharacters. Y K of G is the set of K-defined cocharacters. Here's a definition. Take a subset of X of K, just an arbitrary subset at the moment, a subset Y. We say it's cocharacter-closed over K if it's closed under taking limits under cocharacters. So if you have a point in Y, you have a cocharacter lambda. Suppose the limit exists when you apply lambda to Y. Maybe it does, maybe it doesn't. But suppose the limit does exist, then that limit should also belong to capital Y. Okay, that's cocharacter-closed. And then if we take an arbitrary subset Z of X of K, then we define the cocharacter-closure of Z to be the smallest cocharacter-closed subset of X of K that contains it. That's clear that makes sense. And for the rest of most of the talk, I'm going to be talking about orbits that are cocharacter-closed or not cocharacter-closed, and seeing what this tells us about the situation. So what happens if the field is algebraically closed? then by the Hilbert-Mumford theorem, remember the Hilbert-Mumford theorem says that an orbit is closed if and only if it's closed under taking limits of cocharacters. Yeah. So for an algebraically closed field, an orbit is cocharacter-closed if and only if it's closed in the sense of before on the Zariski topology. So the definition was set up to make this happen in the algebraically closed case. Okay, let this time K a field of characteristic 2. And let's take a field that's not perfect. So take some element A that belongs to K, but whose square root does not belong to K. And let's take SL2 again, equals G. And let's take X to be the matrix. I'll call this G, or I won't call this G. Sorry, I just realized I did something stupid with the notation. Let's call this Z. So this is a point of capital X of K. So it's a matrix. So choose an X and a Y, and the property that X squared plus AY squared equals 1. Suppose you can do this. My action is the conjugation action again. Then I claim that G of K dot Z is cocharacter-closed. Over K. Okay. And that's just a straightforward calculation. With matrices, you can check the only K-defined lambda such that the limit exists is lambda equals 0, the trivial cocharacter. And of course, when you take the limit from the trivial cocharacter, you're not doing anything. You just end up with the point that you started with. So you definitely haven't left the orbit. So this orbit is cocharacter-closed over K, but it's not closed. Or the orbit over K bar is not cocharacter-closed. And the way to see this is you just work out the eigenvalues of this matrix. And you see that the eigenvalues over K bar are X plus A to the half Y. Perhaps I'll write this on a separate page. So the eigenvalues of Z are X plus A to the half Y. So of course you don't see these over the field you started with, because A to the half is not in the field that you started with. Yeah. And it turns out that then the diagonal matrix belongs to the closure. But of course, it's not in the conjugacy class that you started with, because this is in the center. I think I said before that G was SL2. We'd better make. Oh no. This has determinant. This has determinant 1, doesn't it? Yeah. So we're okay. All right. Okay, back to the slides. Okay, question. Is there a rational Hilbert-Mumford theorem? Well, one answer to that question is, well, yes, you set things up so that the Hilbert-Mumford theorem holds, right? So part of the Hilbert-Mumford theorem in this context is saying an orbit is cocharacter-closed if and only if it's cocharacter-closed. We've defined things to make part of the Hilbert-Mumford theorem true. Yep. But there is actually another part of the Hilbert-Mumford theorem that's not vacuously true. You do have to work to get this. So the rational Hilbert-Mumford theorem, take a point X, a K point, then there's a unique cocharacter-closed orbit O contained in the cocharacter-closure of the orbit that you started with. There is one, there's unique. Moreover, you can get there by some cocharacter lambda. Okay, this takes a bit of effort to prove. I was thinking of saying something about the proof. Maybe I will, just very quickly. So what do we have here? We have some point. Let's define R of X to be the dimension of maximal K split torus contained in the stabilizer. Maybe I'll write this. So remember, the stabilizer need not be K defined, right? But it makes sense to write Gx of K. I just mean the K points of G, that K bar points of the stabilizer. So you look inside the K points of the stabilizer, you ask yourself, what's the largest split torus that I can see? And the dimension of that is R of X. And then the idea of the proof is that if the orbit of X is cocharacter-closed over K, then there's nothing else you have to do. You're finished, right? You had to prove that you could get to a cocharacter-closed orbit. If the orbit you're already in is cocharacter-closed, you don't have to do anything. Just take the trivial cocharacter. So suppose it's not. So then there's some cocharacter such that the limit exists. And X prime is not in the orbit that you started with. And then what you do is you show that this quantity R has to have gone up. So you define R of X prime just as I defined it R of X, but this time for X prime, you look at the stabilizer of X prime, you look at the K points, you ask yourself, what's the largest split torus I can see inside there? What's the dimension of that? And you can show that you can choose some lambda to make this go up. Actually, it might not work for every lambda. You need to choose it carefully. And now you look at X prime and you say, is G of K dot X prime cocharacter-closed? If it is, then you're finished. If not, you just repeat the process. You keep on hitting things with cocharacters, keep on going until you get to a cocharacter-closed orbit. So that's the idea. The theorem says that you can get all the way there by taking a limit along just one cocharacter rather than doing this a series of times. So there's a bit more work that you have to do in order to prove the theorem. There's also this question of uniqueness of this cocharacter-closed orbit. Okay, back to the slides. So there's this rational Hilbert-Mumford theorem. And now is there an optimal version of the rational Hilbert-Mumford theorem? And the answer to this question is that we don't know. We think there's one. It would be really nice to have an optimal version of the rational Hilbert-Mumford theorem. There'd be various nice consequences that would flow from that. And we're going to see what some of these consequences are a bit later in the talk. But at the moment, the answer is don't know. So now let's talk about some other results and properties to do with the notion of cocharacter-closure. Firstly, suppose you're in a situation where you have a strong topology. So for instance, suppose K is a local field, or more generally a valued field. And then take a K-defined cocharacter and apply it to some X. Suppose the limit exists, then the limit is in the closure of the orbit that you started with in the strong topology. That's pretty obvious. Cocharacters are continuous in the strong topology. Any morphism is continuous in the strong topology. And a consequence of that is that if an orbit is not cocharacter closed over K, then it can't be closed in the strong topology. Okay, so this notion of cocharacter closed can help you say some things in the presence of extra structure. Just one simple observation I wanted to point out. Now an open question. Suppose we have an X and a lambda, and suppose we apply lambda to the X and we get a limit X prime, and suppose the limit is in the orbit that we started with. Must the limit point be conjugate to the point we started with by some element of the unipotent radical, by some K point in the unipotent radical? And the answer is yes, if the orbit is if the field is algebraically closed. That was the result that I gave you after I talked about the Hilbert-Mumford theorem. The answer is also turns out to be yes, if the orbit is cocharacter closed. But in general, this is an open question. And again, it would be quite nice if the answer was yes. This would be helpful in various ways. So now let's talk about some other properties of cocharacter closure. How does it behave under field extensions? So you start with a field K. Let's take a finite field extension, K prime. We can look at the original orbit, G of K dot X over the small field, but we can also look at the orbit over the larger field. And we can ask, what's the relationship between those two orbits being cocharacter closed? Is it true that the orbit over the small field will be cocharacter closed if and only if the orbit over the large field is cocharacter closed? Well, you need the field extension to be separable if you're going to have a hope of yes, saying yes. The example that I gave you before with that funny 2x2 matrix with the A in, that's a situation where you have an orbit that's cocharacter closed over the small field, but when you pass to the algebraic closure, or just even to some finite purely inseparable extension of the field that you started with, the orbit is no longer cocharacter closed. So the answer is no to this question. This conjecture is definitely no if you're working with non-separable field extensions. So let's assume our field extension is finite and ask this question. And in the forward direction, we call this Galois descent. This is true. I'm talking about separable field extensions. It's not so hard to reduce to the case of a Galois field extension. So we talk about Galois descent. Cocharacter closed over the large field implies cocharacter closed over the small field. What about the other direction? We don't know in general. We think the answer is probably yes. And if we had an optimal rational Hilbert-Mumford theorem, then we would be able to prove that the answer was yes. That would give us a Galois ascent result. We can prove that the answer is yes if we assume that the stabilizer is K-defined. Actually, a slightly weaker assumption will do. But we don't know in general. So now I'm going to change direction a bit. I'm going to talk about spherical buildings for a little while. So let's assume that our group G is semi-simple. What I'm saying makes sense for connected reductive groups, but it's just some things become a bit easier to say for the semisimple case. So let's restrict ourselves to semisimple groups. So the spherical building delta of G. What is the spherical building? It's a simplicial complex with some special properties. And the simplices correspond to the K parabolic subgroups ordered by reverse inclusion. So buildings come with a notion of an apartment. So the apartments are a certain special collection of subcomplexes of the simplicial complex. So what do these look like in this case? Take a maximal K-split torus T of G. Look at all of the K parabolic subgroups that contain this fixed T. So every K parabolic subgroup has got some maximal split torus inside it. Just look at the ones that contain this fixed T and define delta T to be this set of subgroups or the set of simplices corresponding to these subgroups. It turns out that this is a subcomplex of the building, and such a subcomplex is called an apartment. And the reason that these buildings are called spherical buildings is that topologically, these subcomplexes are spheres. You can view them as the simplicial decomposition of a sphere in a natural way. So this is the building as a simplicial object. What I want to tell you about now is a really nice way to construct the geometric realization of the spherical building. Any spherical building, I think any simplicial complex has a geometric realization. You just think of a simplex as an abstract combinatorial object. You think of it as a topological simplex of the appropriate dimension. So you kind of fill in all of these simplices with points and then glue them together along their faces, according to the way that they're glued in the simplicial structure. So these ideas, I gather, date back to Titz and Chevrolet. The literature seems to be a little bit murky on this point. I think the first place I've seen this written down is probably in a paper of Curtis Lehrer and Titz. There's also something very similar done in Mumford Fogarty-Kirwan book on geometric invariant theory. It's called the flag complex there. So let's run through the construction. Take a maximal split torus T of G, and we're going to tensor up. We have yk of T. So by definition, that's the set of cocharacters, K-defined cocharacters of T, or if you like, K-defined cocharacters of G, whose image is contained in T. So this is a free Z module, and you just tensor this up with the reals, and this gives you a real vector space. Next, you define P lambda for one of these lambdas. So remember that we defined P lambda before when lambda was an honest cocharacter. Now we're talking about more general objects, kind of formal linear combinations, real linear combinations of cocharacters. But it turns out that you can still define P lambda. This is quite easy to do. And now you define the so-called vector building. You take the disjoint union of all of these YKTRs. That's what this square union sign means, disjoint union. And the subscript T is indicating that you're doing this over all maximal split tori. So this gives you some very large space. And you factor out by an equivalence relation, tilde. And what does this equivalence relation do? You take a cocharacter, lambda. The equivalence relation glues lambda to G dot lambda, where G is a K point of the corresponding parabolic subgroup, P lambda of K. Okay? And then the set of equivalence classes is this vector building VG of R. There's a natural way to put a metric on VG of R, and then you define delta G of R to be the unit sphere about 0 in VG of R. By 0, I mean the 0 cocharacter or the trivial cocharacter. And it turns out that delta G of R is the geometric realization of delta G. So points in lambda in delta G of R, if you give me a point, I should be able to say which simplex it belongs to, right? And what's the simplex that lambda belongs to? It's the simplex corresponding to the parabolic subgroup P lambda. Okay, This makes sense. This respects the equivalence relation up here, because if you conjugate lambda by some g in p lambda, you're not changing what the parabolic subgroup looks like. P g dot lambda equals p lambda in this case. This space has a natural metric, which it just inherits from the metric on the spherical building. And so there's notions of convexity. You can talk about geodesics. You can say a subset's convex if it's closed undertaking geodesics between pairs of points. You have to be a little bit careful. So remember, the apartments are spheres. And if you take any 2 points in the sphere, there's a unique geodesic, shortest geodesic between them, unless those 2 points are antipodal points of the sphere. So you have to avoid that case. If 2 points are antipodal, then we say that they're opposite 2 points in an apartment. So these are notions that should be familiar to anyone who's worked with buildings. And we have this nice common apartment property. Any 2 points of delta G of R belong to a common apartment. So there's if you're used to buildings as simplicial complexes, then the simplicial counterpart of the statement is that if you take any 2 simplices in the simplicial spherical building, then they belong to a common apartment. This is a counterpart of this statement for points. What that's saying in the language of algebraic groups, maybe I should say, if you take any 2 k parabolic subgroups of G, their intersection will contain a common maximal split torus of G. Now, I want to go back to the geometric invariant theory that we were talking about before, because you can formulate your geometric invariant theory in the language of these buildings. So take some point, little x and capital X of k. So our standing assumption is still that the group G is acting on this affine variety X, and define a set of cocharacters lambda of X. Lambda X is all of the cocharacters such that the limit exists when you apply the cocharacter to X. This is some set of cocharacters. We want a subset of the vector building. Actually, we want a subset of delta G of R. So you just take the image of lambda X inside the delta G of R, and then you take the convex hull of this in an appropriate sense. So you need to fiddle around a little bit. Roughly speaking, you can think of cocharacters as being integer points inside this set of real points. So there's you need to take non-negative real linear combinations in the appropriate sense. So this gives us a subset of delta G of R that we call the destabilizing locus, sigma X. It turns out this is a closed convex subset of delta G of R. Moreover, the orbit that you started with is cocharacter-closed if and only if every point of sigma X has an opposite point in sigma X. So remember, there's a notion of opposite points in delta G of R. If I have a point of delta G of R, it will have an opposite point. In fact, it will have lots and lots of opposite points. So what you're asking for is an opposite point that is still in this subset, sigma X. So in the language of buildings, this is saying that sigma X is completely reducible. This is language that was introduced by Serre. So now I'm going to move away from buildings, but we'll come back to them in a moment. I'll promise you'll, I hope, see the point of this discussion of buildings that we just went through. So let me tell you what G-complete reducibility means. So here G is reductive, connected reductive now. Let H be a K subgroup of G. We say that H is G completely reducible over K if whenever it's contained in a K parabolic subgroup of G, it's contained in a K Levy subgroup of that parabolic subgroup. Okay. Give you a few seconds to digest this idea. So example, suppose G is a general linear group then a subgroup H of G is G completely reducible over K, if and only if it's completely reducible in the usual sense of representation theory. That is, if and only if K to the n is a semisimple H module. So for G equals GLN, this is just the normal notion of complete reducibility from representation theory. I said this before briefly when I was talking about this Clifford's theorem stuff. So this is the theory of G complete reducibility is a way to try to port some of the structure that you see for GLN over to arbitrary reductive algebraic groups. And there's a nice link between G complete reducibility and geometric invariant theory. So remember I said before a while ago now, was one of my examples of actions of algebraic groups, that G acts on G to the n by simultaneous conjugation. So now take a K subgroup H of G and take a tuple H1 up to Hn of elements of H, such that these HIs topologically generate capital H. It's not always the case that such a tuple exists. It depends on the field, but I'm just going to sweep that under the rug. Let's pretend there's always such a tuple. And then this theorem, H is G completely reducible over K, if and only if the G of K orbit of this tuple is cocharacter-closed over K. So this gives a link between complete reducibility and cocharacter-closed orbits. So this was done by Gerhard and Mike and myself over algebraically closed fields in 2005. So this is a generalization to arbitrary fields. And here's a theorem, which I hope will remind you of the Galois ascent and descent results that we had before. Take a K subgroup H of G, take a finite separable field extension K prime. We can ask, is H G completely reducible over K? Is H G completely reducible over K prime? Is there a link between those two properties? And the theorem here says that one is true if and only if the other is true. And the proof is, so you take a tuple of elements that generates capital H, you look at the orbit of this tuple and apply the previous theorem that tells you that H is cocharacter-closed if and only if the orbit, sorry, H is G completely reducible if and only if the orbit of this tuple is cocharacter-closed. And then you use the Galois descent and ascent results from before that tell you what happens under finite separable field extensions. Now, if you're paying attention before, maybe you remember that we had this Galois descent result with no restrictions, but we didn't have a Galois ascent result unrestricted. Okay, so why is it that we can use this result here? And so here's the point of this building theoretic discussion. The point is that you look at the destabilizing locus, sigma H, inside the spherical building, delta G of R. And it turns out that this is not just a subset of delta G of R, it's actually a subcomplex. And then you can use a very powerful result, Titz's center conjecture, which is now a theorem. It was proved about, the proof was completed 12 or 13 years ago now. And what the center conjecture gives you is basically a proxy or a replacement for the optimal rational Hilbert-Mumford theorem that we would like to have, but don't. Remember I said if we have this optimal version of the rational Hilbert-Mumford theorem, this would give us this Galois ascent result. We don't have that, but in this particular situation, we can use the center conjecture. And so we get this nice theorem up the top of the page. So I want to finish, I've just got a couple of minutes left, just by talking very briefly about what we call spherical edifices. So you take a connected linear algebraic group over K, a pseudo-reductive group, for example, or a unipotent group. Construction is not very interesting for a unipotent group, as we'll see. And you just copy the construction of the geometric realization of the spherical building that I was talking about before. You take cocharacters, this makes sense for arbitrary G, you stick them together according to some rule. The rule involves parabolic subgroups. We don't use parabolic subgroups for arbitrary G, we use something slightly different, R parabolic subgroups, Richardson parabolic subgroups. And there are various technical difficulties, but you can still do this. So one difficulty is that the R parabolic subgroups don't form a simplicial complex anymore. And another technical difficulty is that the common apartment property that you had in the case of a reductive group no longer holds. And then finish with a question. Can we use the spherical edifice that we've constructed to do geometric invariant theory for non-reductive groups over arbitrary fields? Work in progress. We don't know. It looks like it might be quite difficult. So that's all I have to say. Thank you very much for your attention.
So we clap online. Questions, comments, please.
So I have some questions. In the Hilbert-Mumford theory, you said there's a unique closed orbit in every GX closure, and can the cocharacters tell us any information about the codimension of this unique closed orbit in the GX closure?
Not that I know of, no. Yeah, I was saying before that the Hilbert-Mumford theorem is a really powerful tool, and I'm trying to sell it to you. I don't know any way of getting this kind of information other than, I suppose, to say in a particular concrete example, maybe you can use the Hilbert-Mumford theorem to help you construct this closed orbit. And then once you found the closed orbit, you can construct it. You can find its codimension. But I don't know of any theoretical way for using the Hilbert-Mumford theorem to get information about this codimension. No.
Okay, so there is a question in the chat. Or maybe a remark. Have you seen it?
The parabolic subgroup corresponding to the cocharacter might give some information. Yes. Remember that there might be lots of different cocharacters that take you to this closed orbit. And so you might get a bunch of different parabolic subgroups. You could ask, well, okay, so maybe you should take this optimal destabilizing cocharacter. That's the natural one to look at. And maybe the P lambda there will tell you something. I guess in the algebraically closed case, when you know that these optimal guys exist. But I still can't think of any concrete way, I'm afraid, to get information about the codimension of the closed orbit.
Okay. Other questions? So please, Zinovi will talk later.
The geometric invariant theory for non-reductive groups that you mentioned, presumably the group would have to be close to reductive for this to make sense. Do you have any perhaps conjectural conditions that would have to satisfy?
I haven't thought about that too closely. As I hinted at the end, if your group is unipotent, then there are no non-zero characters. And so this edifice that you construct is just empty. There's nothing there. So this tells you nothing about orbits. On the other hand, if you have a unipotent group acting on a variety, then the orbits are always closed, right? So you don't need the Hilbert-Mumford theorem at all. So one class of groups where we think things will work very well is pseudo-reductive groups. So for pseudo-reductive groups, the spherical edifice is a spherical building. That was already known. You have the common apartment property, various nice things happen. So I think for pseudo-reductive groups, you'd get a geometric invariant theory that was quite similar to the reductive case for aspects I've been talking about. More generally, I went to a conference a few months ago, and there were people there who were talking about actions of non-reductive groups on quasi-projective varieties, and there was some condition that came up, something like you allowed your group to have a unipotent radical, but you didn't want the unipotent radical just to be a direct factor of the group. You wanted the group somehow to act on the unipotent radical in some non-trivial way. You needed a co-character that did. I think you needed a co-character that acted on the unipotent radical with positive weight everywhere, something like that. So maybe if you have some condition like that, this will give you a nicer theory in this context.
Okay.
Thank you.
Who's next? Who's next?
I have another question. Over algebraic closed field,
Yeah.
You gave an example that cocharacter is not equivalent to cocharacter-closed is not equivalent to closed in a characteristic-2 field. And when characteristic of the field is equal to 0, can we show these two are equivalent, or?
Yeah, in characteristic 0, things are much nicer. So in characteristic 0, or finite field extensions are always separable. So you would hope that being closed is equivalent to being cocharacter-closed, and that turns out that it is.
Yeah, thank you.
Okay.